What we usually think of as angular momentum is known as orbital angular momentum. It describes rotational inertia about an axis of rotation. Thanks to conservation of angular momentum, when this rotating wheel is flipped, I gain orbital angular momentum in the opposite direction to counteract the wheel's change in angular momentum. In a similar example, a cylinder of iron is hung from a string, and an oscillating magnetic field is applied. Just as in the previous example, the metal will begin rotating. This is the Einstein-de Haas effect, which also occurs due to conservation of momentum. At first, this doesn't make sense, since there was no spinning wheel that experienced a change in angular momentum, unless the iron particles themselves were spinning. As it turns out, this idea isn't that far-fetched, since rotating charged particles generate a magnetic dipole. If the electrons in the iron were spinning, then the magnet would have caused the orientation of the angular momenta of the electrons to align with the magnetic field, imparting an opposing angular momentum on the entire iron cylinder to conserve total angular momentum. But several scientists pointed out that electrons couldn't possibly achieve the necessary rotational angular momenta to create their observed magnetic dipoles, so the electrons aren't actually spinning, but they behave as if they were. This phantom spinning property is known as spin, or intrinsic angular momentum. It causes elementary particles to exhibit a magnetic moment and behave as if they're spinning. When measured, unlike orbital angular momentum, spin can only take on discrete values. For electrons, this value can only be half or negative half. Spin has far-reaching implications in the quantum world. It's the foundation of how MRIs work, and it may be involved with how birds sense the Earth's magnetic field.